There are two ways that we can define what an acid and what a base are. The simplest way that we can define what an acid is by the Arrhenius definition. Typically, when acids are written in this way, the chemical formula for an acid will start with hydrogen. When we define an acid as an Arrhenius acid, we're saying that the substance, when it dissolves in water, is going to break apart and form ions. Specifically, Arrhenius acids are going to make hydrogen with a positive 1 charge. Remember that hydrogen is in group 1, and when it loses its only electron, it becomes a positively charged ion. So HCl is a strong acid. When it dissolves in water, it's going to break apart into the two ions that make it up, the chloride anion and the hydrogen plus cation. The Arrhenius definition of a base, however, is a substance that simply produces hydroxide ions when dissolved in water. So when we see a base that's written in the Arrhenius way, typically it's going to end with OH. So sodium hydroxide is made of two ions, the sodium plus 1 cation, but more importantly, the negative part of that ionic compound is the OH 1 minus hydroxide ion, and a base is going to make more of this when it dissolves in water. Some properties that make acids and bases different, well, first of all, our sense of taste. For whatever acids are edible and whatever bases are also edible. Edible acids such as citric acid are going to taste very sour. So typically when acids are weak acids that are safe to eat, they're going to have more of a sour taste. But bases such as caffeine typically have more of a bitter taste, and coffee is probably one of the best examples of that. Another big difference between the way that acids and bases react is that acids typically only react with certain metals to form hydrogen gas. So, for instance, magnesium can be dropped into hydrochloric acid, and by the end of that reaction, it will be fully dissolved. And in the process of doing so, when an acid does react with a metal, it generally will form hydrogen as one of its products. Now, bases react with different types of things. This is why bases are typically used as cleaning solutions, because they react very effectively with oils and fats to form soap in most cases. So potassium hydroxide is a strong base that was used to make the earliest forms of soap from animal fat by reacting the two things together. So bases will typically form soap when they react with oils and fats. When we talk about acids versus bases, we use the pH scale as a relative indicator of how acidic or how basic something is. Water, which is considered to be neutral on the pH scale, has a pH of 7. Anything that has a pH that is lower than 7 is considered to be acidic, whereas anything that has a pH greater than 7 is considered to be basic. Can the pH scale go into the negative range? Absolutely. We'll talk about why that is here in a little bit. And yeah, the pH can go higher than 14. That is absolutely correct as well. But the further you move away from 7, the more acidic something gets, or more basic that something gets, depending on how far away from 7 you are. A strong acid or a strong base is considered to be a strong electrolyte, which means that if something is classified as either a strong acid or a strong base, in this case we'll take a look at the strong acid hydrochloric acid, a strong electrolyte completely dissolves into the ions that make it up. So if something is classified as a strong acid, it's going to break apart into hydrogen plus 1, and it's going to form negative ions, and it's going to fully dissolve when it is mixed with water. But a weak acid has the ability to stay chemically bonded with itself and produces very little free-floating ions when it touches water. The same can be held true for weak bases. Weak bases will form very few ions when they dissolve in water, whereas strong bases will form lots of ions when they dissolve in water. As a quick concept check, we're going to use different symbols to represent the acid that's chemically bound with itself and the free-floating anion of that corresponding acid. I want you to look at these three particle level diagrams and identify the strong acid and the weak acid in each of these diagrams. I'll give you a moment to do that, pause the video, and then hit play whenever you're ready to reveal the answer. If we take a look at these diagrams, the strong acid would be the one that fully disassociated into these small hydrogen +1 ions and the negatively charged anions, whereas the weak acid is the one that only partially broke apart into those two corresponding ions, where most of the compound is still stuck together. This last substance over here is simply just a non-electrolyte, so it would behave neither like an acid or a base in solution. There's very little that we need to memorize, but this is a very important list of the strong acids and the strong bases. There are only 7 strong acids. Every acid that is formed from one of the halogens other than fluorine and astatine is considered to be a strong acid. Hydrochloric acid, hydrobromic acid, and hydroiodic acid. The other 4 strong acids are formed from oxyanion polyatomic ions, chloric acid, perchloric acid, nitric acid, and sulfuric acid. When it comes to our strong bases, every hydroxide of a group 1 metal is automatically a strong base. So it doesn't matter if it's sodium hydroxide or potassium hydroxide, so on and so forth. The other strong bases that exist within group 2 of the periodic table with the alkaline earth metals are calcium hydroxide, strontium hydroxide, and barium hydroxide. Beryllium, magnesium, and radium hydroxide are not considered to be strong bases. There is, however, one other way that bases and acids can be defined. A better way to define an acid and a base is to consider that an acid is a proton donor and a base is a proton acceptor. This definition is called the Bronsted-Lowry definition of acids and bases. In this picture, we can see the ammonium polyatomic ion, NH4. It has a +1 charge. By this new definition of what an acid is, if NH4 +1 loses one of its hydrogen ions, it becomes NH3 without a +1 charge. It's behaving like an acid because it's donating a proton to something else that is accepting that proton. That's considered to be a Bronsted-Lowry acid when something behaves like this. NH3, which is 3 hydrogens bonded to nitrogen with a lone pair of electrons, ammonia can actually accept a proton from something else and become ammonium with a +1 charge. In this case, ammonia is behaving like a Bronsted-Lowry base because it's accepting an extra hydrogen ion from something else to become a new chemical substance. Don't forget that when hydrogen forms its ion, hydrogen by itself is simply just a proton with an electron around the nucleus. So when we say that something is either accepting a proton or losing a proton, hydrogen 1+ is the same as a proton. So that's one very important thing to understand when we talk about proton donors and proton acceptors. This concludes our introduction into the differences between acids and bases. We'll be moving forward into the pH scale in our next lesson.